Log on, tune in, find out. Another good idea from Cambridge.
Means I want to construct objects which with endomorphism algebra is derived equivalent to the Vx. Well, these two objectives are not unrelated. They are related, and usually good generating set for me means I want to construct exceptional sequences. So I give the definition. We say that a coherent sheaf is exceptional if all higher self-extensions vanish and the sheaf is simple, which means that the endomorphism algebra is isomorphic to the field. And we call a sequence of exceptional sheaves, we call this an exceptional sequence. If the following holds, first, all these EI themselves are exceptional. And moreover, I want to have conditions on the X groups. I want that all X groups vanish between all I and j if j is bigger than I, and for all k. So, and I can strengthen this condition slightly. I say that this is a strongly exceptional sequence. If it is exceptional, and additionally I have the following condition. Yes, I have a stronger X vanishing condition. Namely, I want that all higher X groups vanish for all I and j. And exceptional sequence is full if additionally all these sheaves generate the derived category. Yes, okay. Full means I have a generating set, and these conditions are some sort of orthogonality condition if I consider the bilinear form given by the alternating x. Among these elements, I have some sort of orthogonality relation on the derived category, and this is why I consider this as a good generating set. In particular, because of the second thing I wanted to talk about, the construction of tilting sheaves. If I denote, if I have a full strongly exceptional sequence, and if I consider the direct sum of all these guys, then the endomorphism algebra is a finite algebra which follows because essentially because the variety is complete. And by a famous theorem by Bondar, I have tilting equivalence between dbx and the derived category over this algebra. It says that if I take the derived form functor with t in the left argument, going from dbx to db a mod, yes, then this is an equivalence of categories. So, and this is remarkable because this builds a bridge between geometry, X is a variety, and algebra, and in a sense we can understand A as a non-commutative coordinate system for X. Yeah, in a derived sense. Okay, and this is what we are after. And T is a tilting sheaf in a very similar sense as in Klaus' talk last week, only that we do not pass between the derived categories of algebras, but we pass from the derived category of a variety to the derived category of an algebra. So this is a tilting sheaf. Yeah, let me give you some examples to see, some explicit examples. The first example is a classic example by Barlinson, 1979. When you consider X to be the projective space, and on X we have we know many bundles on Pn. In particular, we know following bundles. We have invertible sheaves, Pn, the structure sheaf, and the twisted sheaf T OP1 to OPn. And it is well known that these sheaves form a strongly exceptional sequence. And if you want to know what the algebra is, for instance, for n equals 2, this is has a very simple description. A corresponds to a partial algebra with relations where the quiver is given by has 3 vertices corresponding to O, O1, O2, and there are 6 arrows like this, and if you label the arrows x1, x2, x3, y1, y1, y3, then we have relations xi, yj equals hj, yi for all I and j. So that's a standard example for a tilting object on an algebraic variety. Another example is given by Hürstenbruch surfaces. Which is projective bundle over P1. So this means we have a projection to P1, and we have a section from T1 into Fa. And if I denote F the class of a fiber, the Picard group of Fa, and B the class of a base in Pic, then I get an example of an exception of a tilting bundle given by a strongly exceptional sequence of the form OFA, OFA, F, OFA, A plus 1, F plus B, and OFA, A plus 2, F plus B, and this forms a strongly exceptional sequence. Full strongly exceptional. I will occasionally forget about the full, but always mean full, even if I forget it. And the endomorphism algebra, also very simple. It has 4 vertices, the quiver, like this, between the first and second I have 2 arrows, and between third and fourth I have 2 arrows, and between the second and third I have a plus 2 arrows. And of course there are some relations which I do not write explicitly. Yes, and the last category of Hurst-proof surface is equivalent to the last category of this module, of this algebra. Then, okay, these are the more or less the easiest examples which one can imagine. Maybe only P1 is easier. But in general, it's very unknown whether tilting objects exist on algebraic variety. And of course, there are cases of varieties where we can show that there are no tilting objects in our sense. But we have reason to expect that on a rational variety that exceptional sequences exist. But so far, there's no general method to construct these sort of sequences. And for this talk, I want to look at a very special situation. I want to consider, I want that X be a rational surface, smooth or complete, of course. And I want only to consider these sequences which only consist of invertible sheaves. Okay, one might ask why this special setting, and it's very restrictive and not clear why this should be good. The motivation for this comes from an old conjecture, not old but older conjecture. There was a conjecture, it was conjectured that if X is not a rational surface but a toric variety, then there should always exist a strongly exceptional sequence of invertible sheaves. It was conjectured by King in 1997. At least it was written by him, maybe other people conjectured this too. I mean, this is straightforward a generalization of Barlinson's example, which said that on every toric, every smooth, complete toric variety has a full strongly exceptional sequence of invertible sheaves. But it turned out, that was found by me and Lutzilla 3 years ago, that this is not true. We found a counterexample which was a toric surface. Yeah. This was a bit of surprise because it was a very easy toric surface. You take some Hurst-proof surface, and our example was a blow up of the surface 3 times. And this example was so easy that there are quite some people who didn't believe it. But I think we have now understood this counterexample, and that's what I'm going to talk about. The interesting thing about this kind of conjecture is that toric varieties are more or less combinatorial objects. We can describe them in implicit combinatorial terms, and invertible sheaves on toric varieties we can also describe in very combinatorial terms. And what we actually did is the following. We just wrote a computer program. You can just put everything into the computer. It's rather straightforward, and you let it run and look for tilting bundles. Yeah? It's very straightforward. And but the problem is that you cannot prove the non-existence of sequences because well, it was a combinatorial search. So you find something or not. If you don't find, then you might have to look longer and more yeah, and and we came up with a candidate, and this candidate then we checked by hand, and this was it. But of course, the computer doesn't help you to understand the phenomenon at all. You have to. There has to be some theory, and what I'm going to explain today is that we essentially have understood this problem for toric surfaces and more generally also for rational surfaces. Okay, let me then make the setting more precise. I'm interested in invertible sheaves, so I'm interested in divisors on the surface. So let n denote the rank of the coordinate group on X. X is now a rational surface, and we want divisors d1 to dn in the Picard group of X, which is isomorphic to set n minus 2, such that Ox d1 dot Ox dn form a full, maybe strongly exceptional sequence. Yeah. So first basic fact we need is the following. If I have considered the X between two such sheaves, this is nothing but the cohomology, the case cohomology of O dj times tensor with Ox minus di. Yeah, so X vanishing is nothing but cohomology vanishing for if these are locally free sheaves. And we are now facing a very peculiar cohomology vanishing problem. We have a bunch of divisors, and we consider all possible differences, and we want to have vanishing of all those cohomologies. Yeah, and this, from a computing point of view, this is horrible because the cohomology structure in the Picard group is rather complicated, and you can. This is really complex problem. I mean, this is an exploding problem if you want to take this vanishing of cohomologies. So I try to bring this into a normal form. As follows. Okay, I want vanishing of these cohomology groups here. So if I have some divisor such that all cohomologies vanish, then this implies that the Euler characteristics, this is nothing but the alternating sum of the dimensions, equals 0. Yeah. And this is what I'm going to exploit. So the vanishing set of the Euler characteristic is by Riemann-Roch theorem. This is nothing but the vanishing set of a quadratic form in the Picard group. So by Riemann-Roch, gives us the following thing. Gives us the following. The Euler characteristics is for a rational surface, and the divisor on the rational surface is nothing but 1 plus 1/2 self-intersection of D minus Kx times D, where Kx is the canonical divisor. And now I can, this is a quadratic polynomial, and I can just symmetrize or anti-symmetrize it. If I means if I write this, then I get chi of d plus chi of minus d is equals 2 plus d squared, and chi of d minus chi of minus d, here is the odd part, which is just minus kx times d. And using this simple observation, we get the following lemma. Namely, if d and e are elements in a Picard group, vanishing on whose inverse Euler characteristics vanish, then I have the following two easy to consequences of this. First is if the inverse Euler characteristic vanish, I get the chi of d is equals 2 plus d squared equals minus chi x times d. Second, chi of minus d minus e is 0 if and only if intersection product of d and e equals 1. So that means I have on this, you get some hyperbola in the Picard group, and this has an additivity law, which is very useful. And of course, another consequence is that not only the inverse Euler characteristic vanish if this condition is true, but also the actual Euler characteristics is additive. This is an easy consequence of these three lines. Well, having observed that, I can now proceed bringing an exceptional sequence of invertible sheaves into a normal form. And what I do is I have a condition on the differences, so of the divisors. So what I do is I simply take these differences, meaning I set AI to be di minus di plus 1 minus di for one I between 1 and t minus 1, n minus 1. Yeah. So I take these differences, but now I have to do a little trick to make this thing round and define another element an, which is the difference of the anticanonical divisor, and all ai defined like this. Yeah, that's all I do. And now I look sharply at this lemma, and I get the following properties of a1 to t to an. First property, ai times ai plus 1 equals 1 for all i's. This is cyclically. Yeah. I should have mentioned this. You should have mentioned this as cyclically ordered. Means an plus 1 is a1. Second, ai times aj equals 0 otherwise. And third condition, this is obvious from the definition, the sum of all I from 1 to n equals to minus kx. Yes. If I start with an exceptional sequence and pass the differences at this guy, then I have these properties, and this is my normal form. And I define any set of divisors satisfy this property, this is what we call a toric system. That's by definition, a toric system is a set of divisors I want to IN which satisfy these three conditions. And to every exceptional sequence of invertible sheaves we get such a system. So now we have a name for this and a normal form. And now I should explain why do I call this a toric system. We have started with some rational variety, a rational surface, and so far there was no toric geometry involved. So how does it come? Let me explain to you what a toric surface is. You might know a toric surface or a toric variety in general is an equivariant compactification of an algebraic torus. So if Y is an algebraic surface, then this means I have the action of an two-dimensional torus on Y, such that T embeds as an open orbit itself, and the action just extends the group operation on T. So if Y is smooth and complete, assume then this is a very restricted story. You cannot take arbitrary compactifications and hope that you can continue the group operation on the whole space. So what you essentially get in that case is, if I consider the complement of the torus in Y, then this complement is nothing but a union of curves, where each curve is isomorphic to P1, and this EI form a circle. Not a circle, a cycle, sorry. What is cycle? For instance, if you take P2, then you have a standard torus in P2, and the complement are just the coordinate axis, and I got E1, E2, E3, and the complement is just the torus. And again, these EI are not arbitrary. Actually, the combinatorial description of Y is as follows. Namely, I can completely specify Y by a set of lattice vectors L1 to Ln in set 2, which I assume to be circularly ordered, and such that Li and Li plus 1 form a lattice basis of set. And for every triple of this Li, I have a relation as follows: Li minus 1 plus some Ai times Li plus Li plus 1 equals 0, where Ai is an integer, and there's a one-to-one correspondence between these lattice vectors and these curves Ei. And this relation precisely gives the self-intersection number of this EI. Yes, and there are some more properties of this EI. I have now described the self-intersection numbers. But there are also intersections among the EIs. I showed you already this form a cycle. This means if I have two neighboring EIs, then they should intersect in one point, and otherwise they don't intersect. Means I have the following properties: AI times EI plus 1 equals 1 for all I. Second, E times EJ is 0 otherwise. And also always true for toric surface is that the sum of the EI equals the anticanonical divisor. And this looks very much like the conditions for the AIs on the other breadboard. So we see that there's at least a formal equivalence of these structures. We have divisors on the rational variety, on the rational surface with three conditions. We have the toric divisors. We have the same three conditions, and how do we relate them? And this is very straightforward by linear algebra. There's a direct relation between the AI and the toric surface. What do? I consider what is called a Gale transform. Which is essentially some sort of linear algebra operation. What you do is the following: I consider the short exact sequence. where I put at the left the Picard group of X. In the middle I put Zn, and the co-kernel is Z2. And some divisor D gets mapped to a tuple where all the intersections with the AI of all intersections with the AI. And if now I look at the co-kernel, and in Z2 I get elements L1 to Ln, which are just the images of the standard basis of Zn. And it turns out that this defines truly a toric surface. So what we have achieved now is that if we start with a bunch of divisors, put some conditions on abstract nonsense on these divisors, we derive a toric surface from them. The theorem reads as follows. So the theorem is the structure theorem for exceptional sequences of invertible sheaves on rational surfaces. So if I have OX D1 to OX Dn, an exceptional sequence, of invertible sheaves, so with associated toric system, well, A1 to An, then to this sequence there's canonically associated a smooth, complete toric surface. y of A. Yes, this is one part of the statement, and the main property of this surface is that the prime divisors EI of this surface have the same self-intersection numbers as the AI. Yes. And this is very interesting information because, well, if you look at these relations, then it's more or less clear that you can, instead of giving these integer vectors, you can start giving this sequence of self-intersection numbers, and this cannot be arbitrary. There are strong restrictions what these self-intersection numbers can be. And if we are interested in exceptional sequences, then we have a very strong restriction on the self-intersection numbers on these divisors. And moreover, if you remember from the lemma I had before, this gives us immediate information about the tilting bundle, about the endomorphism algebra of this tilting bundle. And yes, and to complete this statement, in particular, we have the this correspondence establishes an isomorphism of Picard groups. Between Picard group of X and Picard group of Y. Which respects the intersection product. Yes, okay. This is the more general statement. Okay. Now I've given you the structural theorem. I now I give you an example of a toric system in a rather general situation. And this example is, in a funny way, I don't know, it's funny, it's in a strange way, say, related to a root system of which is associated to certain algebraic varieties. You find this, you find the part of the construction, or this construction you find in the book of Manin on cubic forms. In one chapter of this book, he considers a variety, which is a blow-up of P2. Yeah, the P blow-ups, Bt to B0, B1. And he's interested in the divisors which have the property that the chi of D, the following set of divisors, that the Euler characteristic and the inverse Euler characteristic both vanish, and for the case he considers the case t smaller equal 8, I think, and then it turns out that these divisors form a root system in the Picard group. Yeah. And how can you identify the root system? Well, what he does, he defines a set of divisors here that A0. Sorry, I should give you some more information before. Yeah. Okay, this is a blow up of P2, and we want to specify some set of vectors in the Picard group. So this is best done if you have a good basis for the Picard group. And there's a very nice basis in this case. Say namely it's given by elements H and R1 to RT, where H is the pullback of a class of a line on P2. And the Ri are the total transforms of the exceptional divisors of the blow-ups. Yeah. And with this data, we can right now define a special set of divisors in the Picard group, which are contained in this set, namely A0 is given by I should first say something more, sorry. Okay, why is this a nice basis? We have the following property. The self-intersection number of A is 1. The self-intersection number of Ri is -1 for all I. And otherwise there are no intersections. This means that this basis diagonalizes the intersection product in the Picard group. That's very convenient. And now I give you the special set of divisors I meant before. I set H0 to be H minus R1 minus R2 minus R3. A1 or AI is Ri minus Ri plus 1 for all I between 1 and t. And then I draw a diagram whose vertices are given by the II, and the edges are given by I draw an edge even only if AI times AJ is non-zero. And if I look at this and this definition, then I get the following diagram. Which you probably know better than me. You get some diagram of this type En, which is of course in Marnik's book you find only the most 8, but you can write down this an arbitrary length. Here we have sitting A0, A1, A2, A3, and so on up to T minus 1. Okay. So and it turns out that this root system is a root system corresponding to a cube of this type. Now, how is this related to toric systems? I claim there's a toric system related to this. How do I get this toric system? Well, what I do, I throw away A0. I cannot use A0. And I have to add some more divisors, but not too many. So I replace by the A0 by the following divisors. AT simply RT, AT plus 1 is H minus the sum of all the Ri. Yeah. So it looks a bit like x0, but I take here, subtract all of the Ri. At plus 2 is H, and At plus 3 is H minus I R1. So essentially what I have done, I replaced A0 by 4 other divisors, and I get that now A1 to AT plus 3 form a total system. Yeah. So you just take the conditions I want over there. And the funny thing is, I mean, I've given the definition of total system abstractly. It's not clear that, and indeed it's not true that every total system should come from the exceptional collection. But this one does. It comes from the collection an exceptional sequence. Of a very simple form. Simply Rx R1, Rx R2, OH, O2H. And this is always an exceptional collection. And in some way, this kind of root system in a mysterious way is also related to some exceptional sequences. But I have no idea whether this is significant or not, or accidental, but it looks interesting at least. And one more fact is if these blow-ups commutes, means if I blow up in a sense simultaneously, then this is even a strongly exceptional sequence. Okay, yeah. If you like to see the quiver would look like this. I have 3 arrows here, and for every R, I make a note here, and then, yes, I have arrows like this, and so on, until here. Modulo some relations, which I cannot remember now. And there's a general quiver coming from this kind of total system. Okay. Now let me now state the main results. The first result is simply existence. I've shown you if X is a blow-up of P2, then this procedure gives an exceptional collection for this X. And the same statement is true for varieties which are blow-up of some Hirsebruch surface, and we know that every rational surface is either a blow-up of P2 or of a Hirsebruch surface. So the first theorem is that every rational surface, smooth and complete of course, admits an exceptional sequence of invertible sheaves, a full exceptional sequence. Actually, that's not a new result. This follows already from results by Orlov. So, but it comes very conveniently out of our formalism and gives a bit, for our context, and we have a nice explanation for this. The other result is the following. Yeah, okay, we know every rational surface admits an exceptional sequence, but we do not know whether it admits a strongly exceptional sequence. That means we do not have any general construction of tilting objects, but we have a criterion for tilting objects consisting of line bundles on rational surface, which says any smooth, complete rational surface which is not P2 admits a full strongly exceptional sequence of invertible sheaves if and only if, no, if, not only if it can be obtained by blowing up a Hirschsprung surface at most 2 times. So what does it mean? We can blow up twice, but we can blow up possibly in several points. Yeah, we are allowed to blow up any zero-dimensional subscheme or subvariety. We can blow up once or twice, and then we still get a strongly exceptional sequence, which means a tilting object. And yeah, that's slightly non-trivial. If you are given some rational surface, there might be more divisors than you need to blow down to a Hirschsprung surface, and not every possibility to blow down satisfies the condition. So in general, you have a problem to identify the right sequences of blow downs to get to the Hirschsprung surface. It's not clear that you might, if you do it the wrong order, you might need more steps than more than 2 steps. Okay, and the other main result is that the converse is true for toric surface. So the other theorem, then any smooth complete toric surface admits a strongly, okay, different from P2, a full strongly exceptional sequence of invertible sheaves if and only if it can be obtained by blowing up a Hirschsprung surface at most 2 times. Yep. We believe that this converse is also true for general rational surfaces, but we cannot prove it at the moment. So, but it suggests that there that there is a general some geometric restriction on the type of tilting objects, and that's interesting. If you look at our counting example, which we gave, There's a minimal example which contradicts this condition. Yeah. If I okay, now I assume that you know toric geometry, but it's more or less end of talk, so don't worry. If this is the set of integer vectors for the Hirscherhof surface, and our counterexample was given by blowing up 3 times, and it looks like this. And if I note the self-intersection numbers of the invariant divisors, these are like this: -2, -2, -1, -3, -2, 0, and 1, I think. Looks like this. And now, if I blow down, I get this there, -2, 0, -3, 1, -2, -1. So I only allow to blow down -1 divisors, otherwise I get singularities. And I can blow down once more. Sorry. So I get 1, -1, sorry, should be -2, -1, -2, 0. So see, I've used up all possibilities, and I ended up with a toric surface which is not a Hirscherhof surface. So, and the theorem now states that this toric surface does not admit a strongly exceptional sequence of invertible sheaves. However, if I blow up this surface, I do it here. Once more, I consider the same fan, the same set of integer vectors, like this. But now I blow up here. It means there's a bigger toric surface. Then I get some slight change in the self-intersection numbers. I get -1, -1, -2, -3, -1, -2, -2, 1. No, 0. Now I can do something different. Now I can Now I can plow down these 2 arrows, this one and this one. I end up with a fan like this: -1, -2, -2, -1. Now I have still 2 ways left which I can eliminate. So I do this, and I end up with the fan like this. They have self-intersection numbers 0, 1. Hopefully I'm not wrong. So I think it's correct. So, and this describes the Hirscherhof surface, and this means by the theorem, this toric surface has an exceptional collection of invertible sheaves, and this related to what I said before, the way I can blow down a surface is not unique to get a minimal model, and here I could have chosen something else, yes, and in this case I just got some more degree of freedom which allowed me to get down quicker than in this case, and so here I have something, there is nothing. Okay.
Thank you very much. Are there questions, comments?
Can you characterize the algebras which arise this way?
Well, with the Euler characteristics, I have some control on the dimension vectors here, dimensions involved here. The number of errors is the Euler characteristic of some AI, and I know that this is additive. This was the lemma from the very beginning, and that means I know I have if I have here I have let's take this one. I have 2 here and 3 here, means I have 6 paths, and but by this condition the dimension vector, the Hom vector between these 2 must be 5, so I have one relation here. So this is some general thing we can say. Another thing is that okay, these are hidden in these figures is a toric variety. I mean, by our structural theorem, there is a toric variety somehow in there. I have no idea if this has some consequence for this type of figures, but it's an interesting fact at least. But so for more I cannot say because these algebras simply to be difficult, I would say. Yeah, otherwise. But they have some intrinsic toric structure, even if they're not coming from a toric variety.
Further questions or?